Everyone, today we'll have the second class of superconductivity. Uh, so, in the last class, we discussed about what exactly superconductivity is and the conductivity formula for a metal. Then, what happens in superconductivity, the scattering of electrons with the phonons, and what was the phonon, like all those things. Today, we'll talk about, before starting the class, I'll just give you one statement that superconductivity state is an ordered state. Means here the electrons are very ordered. That means if I say you the ordered state, the first thing that strikes your mind is about entropy. You study about disorderness by entropy. So that means the thermodynamics has a big role to play in superconductivity, and that we'll discuss in next or maybe the next of the next class. Okay, so here we are talking about an ordered stream of electrons. Okay, that thing can be done later. There might be a confusion between the perfect conductivity and the superconductors. So you just don't consider that a perfect conductivity or a perfect conductor is a superconductor. No, because to have superconductivity, it should be a diamagnetic system below Tc. Okay, I'll give you an example. Suppose you have a metal, a perfect conductor. Okay, this is a perfect conductor, and we'll talk about two processes. One is called ZFC and one is called FC. Okay, ZFC means zero field cool and FC means field cool. So what we'll do here in ZFC, we'll allow this metal perfect conductor to cool down and come down below Tc. Tc is the critical temperature. Okay, at zero magnetic field. That means we'll not apply any kind of magnetic field there. And in the FC process, what we'll do, we'll let this perfect conductor cool down at some external magnetic field. Okay, so we'll do this thing on a perfect conductor and a superconductor, and we'll check out what is the difference between them. So what happens if a perfect conductor is, suppose this is a perfect conductor, suppose it's cooled down, we are cooling down. Okay, it's cool down, cooled, and then now it is at a very low temperature. Okay, and suppose now we are applying magnetic field from outside. Now initially B was 0, B external was 0. Now we are applying magnetic field from outside. That means B is greater than 0. So what will happen? So this perfect conductor will expel all the magnetic fields that you are trying to put inside. That means it will not allow the magnetic field to enter the metal. Very much like superconductor, isn't it? So why it's happening actually? Actually, see, metal, that means there is a flow of current. You have these free electrons, perfect conductor. So we have free electrons. There is a flow of current. Okay. Now when you apply magnetic field from outside, earlier it was 0. That means you are changing the flux or the lines of force passing through the metal. And one thing is very known, and that is AD current. We know about AD current. And AD current, what it does, it doesn't allow the change in flux. So the moment initially the field inside was 0, the flux was 0. The moment you try to put some flux inside the metal, the perfect conductor, the AD currents will come and will just eliminate the flux from inside, ultimately making it 0. Because AD current doesn't like any kind of changes. Okay, so that happens at ZFC. Now what we'll do, we'll now apply the same metal, the perfect conductor. Now we'll have some external field initially. Then we cool down. Initially the lines of force are penetrating the perfect conductor. Now we cool down. Okay, now we cool down, and now what we are doing, we are removing the external field. Okay, the field is removed. What happens? There is still lines of force inside the metal. Again the eddy current. The eddy current doesn't like the change, as I told you earlier. So the moment you change the flux from a value to a zero value, the eddy current will develop there, because we know that change in flux will give you the induced EMF. Okay, eddy current will develop there, and they will again maintain the magnetic field inside the system. And this magnetic field will not die off, because we are talking about perfect conductor. That means the resistivity tends to zero. That means this current will be there forever. That means the eddy current will be there for forever. So they again maintain this magnetic flux inside the metal. But this is not the thing with superconductor. This doesn't happen in superconductor. That means if you now take a superconductor, now no matter you apply the field first and cool down below Tc and then apply, or the initial field was zero, then you cool down and again apply the field, the final result will be in superconductor, the final result in superconductor, that it just don't allow the lines of force to pass through. That means what's exactly happening here? Why they are not allowing the lines of force? So the explanation of eddy current will not work here. So something else is happening. There might be the reason of Cooper pair. I haven't told about you Cooper pair. Okay, I'll just give you one hint, or just idea of what is Cooper pair. The only phenomena where an electron attracts another electron. Okay, I will give you the full explanation in the next part, but it is the only phenomena where an electron attracts another electron. That is the formation of Cooper pair. And you know from that if you have two electrons in a cell, and if they both are oppositely spin, okay, satisfying Pauli's exclusion principle, if they are opposite spin, then they will give you diamagnetic system, isn't it? Something like that happening here in superconductor. So we'll talk about Cooper pair in the next class. For now the moment, that means superconductor, irrespective of ZFC or FC, they show the same result. And that's why superconductivity is a reversible process. That means no matter you first apply field and cool down, or you initially the field was zero, then you cool down, then you apply the field, the result will be same. So they are showing the reversible process. Whereas the perfect conductor will show superconductivity activity in the first case, but in the latter case, when in the FC, they will show their own behavior, and that's where you can distinguish between perfect conductor and superconductor. So superconductivity is not about only perfect conductivity, but it is also about having diamagnetic nature no matter what is the history. Okay, that means the Meissner effect. Okay. Now let us talk about the magnetic field. Okay. Say, when I am saying you that magnetic field, that it should be diamagnetic system, or suppose you have a superconductor in some, and by mistake you put, suppose you have prepared a superconductor of mercury, and by mistake you just put 1% of iron there. Somehow iron was just doped 1%. Earlier we talked about the critical temperature of superconductivity is 4.12 Kelvin. Now if suddenly you put 1% of iron there, its critical temperature will fall down around 0. something Kelvin. Okay, that means you are destroying the superconductivity property. Okay, that means the magnetic element will destroy the superconductivity. That's why we'll never use magnetic element in superconductor. There are two types of superconductor. I have told you type 1, type 2. We'll discuss today type 1, type 2. And another thing we should remember, one is called elemental and one is called alloy. Generally, type 1 superconductors are elemental superconductors. Elemental means made of single element like mercury, copper, those kinds. And alloy means you have different compositions there. Definitely type 2 superconductors will give higher critical temperature. We'll discuss today how it will be. Okay. Now, I'll draw one graph for you. Okay. Suppose this is critical field. Now, what is critical field? I'm just going to explain you. And this is the temperature. Okay. Now, I'm getting a graph like this. Okay, it's touching here. Sorry, let me clear it out. It's touching here. Okay, it's point. Okay. This is the graph between critical field versus T, and this point is TC, critical temperature. Okay. What happening here? Actually, at critical temperature, now what is this critical? What is this magnetic field? Now, your system, according to Meissner effect, your system should be a diamagnetic below Tc. Okay, that means in a superconducting state, it should be a diamagnetic material. That means no matter how much magnetic flux you try to apply from outside, there will be no lines of force entering the system. Okay, but suppose you have started to increase the applied magnetic field. That means suppose you have a superconductor and you are suppose you have a superconductor, that means below Tc, and initially you suppose applied 1 Tesla field. No lines of force are entering the system. Good. Now suppose you increase that field by 2 Tesla. Now there may be a case that some lines of force will enter the system. Okay, some lines of force will enter the system. There may be a case. And suppose you increase the field even higher, 3 Tesla, then there are cases that where the magnetic lines of force can enter the system and destroy the superconductivity. That means along with Tc, the critical temperature below which the conductor can be a superconductor, there is a value of Hc. That means there is a critical field above which if you apply the magnetic field, then it will again destroy the superconductivity because it will no longer remain a perfect diamagnetic system, not satisfying the Meissner effect. That means along with Tc there is a Hc, critical field, above which you cannot apply magnetic field. If you go beyond that Hc, then the system's diamagnetism will be destroyed. So this is the graph of Hc versus temperature. Now see, at Tc, the critical field has a minimum value here. That means suppose for example we have a mercury superconductor, and I am applying, and suppose 1 Tesla is a critical field at Tc. Means at 4.212 Kelvin, if I apply 1 Tesla of magnetic field, then there will be no entering of lines of force inside the mercury superconductor. But if I go beyond 1 Tesla, 1.1 Tesla, then lines of force will enter the mercury superconductor. No longer remain a superconductor. That means at Tc 4.12 Kelvin, the limit is 1 Tesla. That means the value of Hc will be 1 Tesla at Tc, which is the minimum value. Now suppose you come down below temperature, means 4.12 Kelvin is for superconductivity. Na? Suppose you come to 3 Kelvin, suppose here somewhere, 3 Kelvin. Now at 3 Kelvin, you are allowed to apply a magnetic field higher than 1 Tesla. Because see, this point has higher value than this point. So that means now you can apply suppose 2 Tesla. Even in 2 Tesla, the lines of force will not enter the system. Again, if you come here, little higher than this, then maybe you can apply 2.2 Tesla. And at T is equal to 0 Kelvin, the value will be the highest. The graph is little, it should be like this, just go up, okay. So at T is equal to 0 Kelvin, you can apply the highest magnetic field, and that will be the highest value of Hc. Means at T, suppose you have T is equal to 0 Kelvin for mercury, then suppose you can apply 4 Tesla. And even at 4 Tesla, there will be no lines of force passing through the system, or the diamagnetism will be not lost. But at Tc, that value is 1 Tesla. That means with temperature, the value of Hc will change. and we have a formula for that. You don't need to know the derivation at present. You just can have this formula which states Hc is equals to H naught 1 minus 1.07 T by Tc whole square bracket close. H naught is the magnetic field at T is equal to 0 Kelvin. That means the maximum possible value of critical field for a system. That means H naught is this value at T is equal to 0 Kelvin. Okay. So you have Hc is equal to H naught 1 minus 1.07 T by Tc whole square. T is the temperature at which you are determining the critical field, that how much I am allowed to apply, and Tc is the critical temperature of the system. If T is equal to Tc, that means you have 1 minus 1.07, isn't it? A negative quantity. That means it's not applicable at T is equal to Tc. Less than T equal to Tc, you can go with this formula. Okay. So remember this formula. Now, let us, that was the case for a type 1 superconductor. Now I will tell you what is type 2 superconductor. Similar Hc versus T graph will check in case of type 2 superconductor. But before going to type 2, let us understand what is type 2 superconductor. Now, till now we are talking about Meissner effect. And in the last class, I calculated one thing. The susceptibility is negative. I have shown you. The susceptibility is negative. That is diamagnetic system. For example, if I write B is equals to total magnetic flux induced is equals to applied field, plus if you are doing in CGS system, you will write 4 pi m. M is the magnetization. And B is equal to 0. That means you get minus 4 pi m is equals to H. Or if you are doing in SI system, then you simply have m minus m is equal to H. Because in SI system, B is equals to mu naught H plus m. So if B is equal to 0, H will be equal to minus m, or minus m is equal to H, the same thing. Minus m is equals to H. Okay. So in many books, if you see, you will get in the y-axis as minus 4 pi m and H in the x-axis. Okay. So minus 4 pi m is equals to H. So if I remember the straight line equation, that was y is equals to mx plus c. So intercept is 0 here. Gradient is 1. If this is y, this is x. Y is equals to mx. That means if I plot a graph between minus 4 pi m and H, minus 4 pi m, and this side I have H. If I plot a graph between these two, I get this kind of thing. Okay? A straight line, no intercept, so you're passing through the origin. Okay. This is in case of a superconductivity, when it is diamagnetic. After superconductivity, suppose if you cross the applied field cross the critical field, then it becomes normal system, normal conductor. That means this will be finished here. This property is still this point, and this point is critical field, critical applied field, Hc. That means if your applied field crosses Hc value, then this directly proportional characteristic will be lost, because then it will be no longer diamagnetic system. It becomes a normal conductor. Then the property will be different. So here we have outside this graph, right side of this point, we have normal conductor. Here it is superconductor. Okay. This is purely a graph for type 1 superconductor. Then what happens in type 2 case? Type 2 superconductor is little more interesting. Let me draw the graph first. Okay. Y-axis is same, minus 4 pi m in CGS system. X-axis is your H. x-axis is your h. So what we'll have here, first it will increase like this, like type 1 superconductor. Then it should have come like this. Suppose this is HC. Let me write HC1. But it will not come like this. It will go like this. A kind of a parabola and touches suppose here. And let me note this pointage. HC2. Okay. That means from HC1 to HC2, what's happening? See, from HC1 to HC2 is no longer a straight line equation. It's like a parabola, it's falling down. Okay. That means the system is now perfectly diamagnetic. And this state is known as vortex state, a mixed state. A vortex state. Vortex. A mixed state. Okay. And this, if a system, and between this SC1 to SC2, the system is still a perfect conductor. Okay. But lines of force are entering the system. Okay. The lines of forces are entering the system between SC1 to SC2. Some lines of force will enter the system. That means it is not completely satisfying the Meissner effect, but still it is a perfect conductor, but it is not satisfying the Meissner effect. And they are known as type 2 superconductor. In some books you might named as hard superconductors. Type 1 will be a soft superconductor. Soft because they have a limited critical field value, limited TC value. Okay. And this is known as hard superconductor because you can go beyond the first critical value as well, first critical magnetic field value as well. Okay. And if you want, you can calculate the average value of C. This is the average value. Just extend this and bring it. You can write HC here. Okay, the value between HC1 and HC2. Okay. So this vortex state is very interesting state. Okay, we'll discuss about it later. So now for this graph, you know this is type 1 superconductor. And for type 1 superconductor, the relation between critical field and temperature is this. Then what will be the graph for type 2 superconductor in which this Hc varies with temperature? So what we'll have here, we'll have this kind of a graph. This is Hc, this side you will write Hc, this is temperature. So critical TC value will be same. It's not like that TC1, TC2 will have a same TC value. This is for first HC1 value. This is your HC1, and then you will have this is your HC2. This graph should be like this, no? HC2. So this value will be HC2. This value is HC1. Two critical magnetic field. That means in type 2 superconductor is allowing you some extra applied magnetic field, which was not allowed in case of type 1 superconductor. Very interesting, isn't it? Okay, that thing is done. So what we have learned today? We have learned the superconductor shows a reversible process and how they are different from a perfect conductor. Then we discussed about the relation between critical field and temperature in type 1 system. Then we got a formula, okay, that works just below TC when T is less than TC. Then we draw a graph using a straight line equation for type 1 superconductor. Then we define the type 2 superconductor, and there we define the system called vortex state. Okay, where the system is not completely satisfying Meissner effect because it's allowing some lines of force to enter the system, but it's still maintaining its superconductivity. That means type 2 will not satisfy Meissner effect, but it's still a superconductor. Okay, it's still a superconductor. How much the lines of force will enter, penetrate through the system, that we'll discuss later. Now, so this is very important. This thing this graph, and the first, that critical field versus temperature for type 1, those are very important things. Okay, and in the third class, maybe we'll in the fourth class or maybe third class, we'll talk about the thermodynamics of the magnetic field as well, superconductor as well. Okay, now I'll leave you with one question here. You just think about it. In the last class, we talked about that if the resistivity tends to 0, then what happens to Maxwell's equation, Maxwell's third equation, where we had del cross E is equals to del B del T minus del B del T, and if the resistivity tends to 0, that means electric field tends to 0, equals to 0, that means del B del T is equals to 0. Okay, if the magnetic field is initially 0, then there is no problem. But if magnetic field is not 0, that means what this equation is saying us? It is saying us that with time magnetic field cannot change, because B is constant with respect to time. That's equal, no? So with time magnetic field cannot change inside the superconductor. But if you remember today's first discussion, it was like this, na? Here in superconductor, before TC, the lines of force can penetrate a superconductor, no problem. The moment you cool down the superconductor below TC, the lines of force inside is 0. But just if you use the Maxwell's third equation, the change of B with T is not allowed. But here it's changing. Initially there was the value of B inside superconductor, not superconductor, normal conductor, higher than TC value. But if you decrease the temperature of system to a superconducting level, then the inside the magnetic field is 0, which is not allowed by the Maxwell's third equation. That means we need to define some new equations for superconductor, because that Maxwell's equations are not working for this, because they are just not allowing B can become equal 0 inside superconductor. Okay, so that's for that we'll define a new set of equations, two equations known as London equation 1 and 2. So in the next class, first thing we'll study, that is London equations, very interesting equations. Then I'll talk about little about the Cooper pairs. Okay, someone asked me about quasi-particle, that what is quasi-particle. In the last lecture I did say about quasi-particle, that they are I give an example of phonon, the quasi-particles. So in solid state physics, when we need to define vibrations with some quantized character, then we use these quasi-particles. Sometime you heard about phonon, sometime you heard about exciton. For example, the electron. Let us talk about electron. An electron moving freely and an electron moving inside a solid, their masses are different. One mass is known as effective mass, another freely mass is the race mass that we know. Okay, so the effective mass depends upon what? K vector and all those things. You know the formula, no? M star, effective mass. So that means the electrons inside the solids is different. So if you need, so that electron is also can be, we say, a quasi-electron. Okay, a quasi-electron, because that character you cannot determine outside the solid. So if you take out the electron outside the solid, they become a normal electron, no longer a quasi-electron. In the last class I told you the quasi-particles cannot be taken out from the system. It's not like we can have, if we have photoelectric effect where the photons are the light's quantum particle. So then similarly for a sound or heat, we talk about phonon, a quantum particle. It doesn't mean we can have a phonon electric effect, because for that the phonon has to come out. The moment it's come out, it's just a meaningless thing. It's a theoretical concept. Okay. Similarly, electron inside the solids, they are quasi-electrons because they have effective mass, which is different from normal mass. The moment you take the electron outside to judge, it is quasi-particle or what, it's finished, because outside the solid it becomes a free particle, free electron. Okay. So the quasi-particle means in solid state physics, when we talk about vibrations or something like those things, we assign some quantum concept to them, and then we use this quasi-particle concept. The phonon is one of the example of that. Okay, hope you like this class. So just think about the Cooper pair, the only scenario where the electrons can attract electron directly or indirectly. That we'll talk about in the next class. Till then, just think about. And if you need any kind of, please do comments your questions here in my link, and please like the page, as everyone says in the YouTube page, that like and comment and subscribe the page. If you think that my classes are good enough, then you can subscribe me, so that whenever I upload the next class, you'll get the link, isn't it? Thank you very much for today's patience. Hope the lockdown is going well. Be safe, be happy, stay at home. Thank you very much.